In this video, we're going to start talking about global or absolute mins and maxes on closed and bounded intervals. So in the last video when we did example 1, we were finding absolute extrema of a function, but we were looking on the entire domain. So remember, that actually made it a little bit more complicated. We had to follow those same steps that we used for local mins and local maxes with that tiny extra thing at the end. But what's nice about this is if we do this on a closed and bounded interval, the process is actually quite a bit easier. So we don't even have to worry about the first derivative test now. So here, if we do it on a closed bounded interval, then all we have to do is find all the critical points of the function on that interval, evaluate the function at each critical point and at both of the endpoints. Okay? And then step 3 here, not really even a step, just the largest value is the max, the absolute max or the global max, and the smallest value is the absolute or global min. Okay? So that's pretty much all there is to it. This kind of goes back to the extreme value theorem from a few videos ago. So remember, the extreme value theorem basically says, gives you conditions under which, you'll have global mins and global maxes, and it tells you global mins and global maxes, they're going to happen at critical points or at one of the endpoints. So that was a few videos ago. You can check that out for more details if you'd like. Anyway, let's go ahead and go through this example here. So find the absolute extrema of g of x equals x to the 2/3 times the quantity 9 minus x squared on this closed bounded interval from -1 to 8. So, step 1, find all the critical points of the function on the interval. Okay, so we don't really have to worry about domains so much here. I guess we kind of should check it just to make sure, but for all the ones that we'll do in these videos here, we won't have to worry about domains for stuff like this on closed bounded intervals. Because the idea is that, if we're restricting ourselves to an interval, then the function should already be defined on that whole interval, so we shouldn't have to worry about domain restrictions. But it's always a good idea just to check, just to make sure nothing crazy is happening. But anyway, we won't do anything like that in these videos, and I've never seen anything like that come up in any classes that I've taken or taught. So anyway, all right, step 1, find all the critical points. So that means find the derivative and set it equal to 0, solve for x, and also figure out where is the derivative undefined. So let's go ahead and find the derivative here. So let's see. G of x equals x to the 2/3 times the quantity 9 minus x squared. So kind of a nasty function, not too bad I guess, but could be a little bit nicer. So we'd have to do a product rule here, but so here's our first function, and then here's our second function, 9 minus x squared. But actually, let's go ahead and distribute the x to the 2/3, so it'll make it just a little bit simpler. Not a whole lot, but just enough to make it worth it. So if we distribute this x to the 2/3 into here, then this is going to be 9 times x to the 2/3. Alright, and then minus x to the 2/3 times x squared. So remember, if you have the same base, you just add the exponents, right? So x to the 2/3 times x squared is x to the 2/3 plus 2. Okay, so 2/3 plus 2. Remember, 2 is 6 over 3, right? 6 over 3. So 2/3 plus 2 is 2/3 plus 6/3, which is 8/3. Okay, so our exponent here is going to be 8/3. So this is 8/3. Okay, so x to the 2/3 times x squared equals x to the 8/3. So that's just an algebra thing there. Okay, so here's our function g of x. Okay, so this is g of x. Now, this is nice because when we do the derivative, we don't really have to worry about a product rule. Okay, our product's gone now, so that's nice. It's a little bit simpler now. So let's go ahead and find that derivative. So g prime of x equals, now it's just power rule, right? So 9 times 2/3 x to the negative 1/3. 2/3 x to the negative 1/3. Okay, that's what we get from this first term here. And then minus, so this is going to be, when we take a derivative, we get 8/3 x to the 5/3. So this is 8/3 x to the 5/3. Okay? So that's what's happening here. So let's go ahead and simplify this a little bit. 9 times 2/3, that's going to be 6. Okay, so 3 goes into 9 3 times, then 3 times 2 is 6. So this is 6, and then let's write it like this, x to the negative 1/3. We can write that as x to the 1/3 with that on the bottom. Okay, so remember, negative exponents, if they're on top, you push them on the bottom. Okay, so also just an algebra thing there. Alright, and then minus 8/3 times x to the 5/3. So minus 8/3 x to the 5/3. Okay, so now what we should do is get a common denominator to make everything a little bit simpler. So denominator here is x to the 1/3. Denominator here is 3. Okay, so our common denominator is just 3 times x to the 1/3. Okay, so that's that's our LCD. Can't get any simpler than that. So we're going to multiply this guy by 3 over 3, and this guy by x to the 1/3 over x to the 1/3. So let's come up here, where we have a little more room. So this equals 6 over x to the 1/3, and I'll leave a little bit of space here just so we can show all the details here, and then minus. Let's write this as 8x to the 5/3 over 3. 8x to the 5/3 over 3. All right, so we'll just show more of the details for the algebra. Why not? Okay, so remember, to get a common denominator, we multiply this guy by 3 over 3. And we multiply this guy by x to the 1/3 over x to the 1/3. All right, so now they have the same denominator, 3x to the 1/3, 3x to the 1/3. Good. So when we simplify on top, 6 times 3 is 18. And then what happens over here? 8x to the 5/3 times x to the 1/3. So actually 5/3 plus 1/3, that's 6 over 3, which is 2. So this is good because this becomes 8 times x to the 2, okay, or 8x squared. Okay, so remember, if you multiply things like this, if they have the same base, then you just add the exponents. So x to the 5/3 times x to the 1/3, that's x to the 6/3, which is x squared. So 18 minus 8x squared. All right, and then all that's being divided by 3x to the 1/3. All right, so now so here's our derivative here simplified. So this is nice, this isn't too bad to work with. So we just have to figure out where is this derivative 0 and where is it undefined. Okay, so first of all, it's undefined if we divide by 0, right? So we have a division here, it's a fraction, so top and bottom. So this is undefined when the denominator is 0, and the denominator is 0 when x is 0. Okay, so this does not exist when x equals 0. All right? But remember, to be a critical point, you also have to be in the domain of the original function. So is x equals 0 in the domain of the original function? Well, let's go back up to here. If we plug in 0, what happens? 0 to the 2/3, well, that's okay. Okay, we can raise 0 to the 2/3. Sure, that's fine. That's just 0. And then 0 squared is 0. So what we have is 0 times 9 minus 0. So actually, if we plug in 0 for x, we just get 0 back. So that's fine. That's totally fine. 0 is in the domain of this function. And also, it's in this interval, right? We're okay with that. So 0 is part of this interval, so we don't throw it out. Okay, remember, we're only looking on this interval here. Anything outside of the interval, we don't care about. But 0 is in the domain, and it is in this interval, so we're good. So that's one of our critical points. This is one of our critical points here. Okay? X equals 0 is one of our critical points. Now we also have to figure out where is this derivative 0. So remember, if you have a numerator and a denominator, the whole thing equals 0 when the top equals 0. So let's come up here where we have more room. So 18 minus 8x squared over 3x to the 1/3. Okay, remember, this equals 0 when the top equals 0. So all we have to do is just set the top equal to 0 and solve for x. So 18 minus 8x squared equals 0. Okay, so if we solve this for x, a few different ways to approach it, but let's go ahead and do this. Let's say add 8x squared to both sides, so 18 equals 8x squared, right? And then let's divide both sides by 8. So let's come up here, running out of room. Let's divide both sides by 8, so 18 over 8 equals x squared, all right? 18 over 8, that simplifies to, if we pull out a 2 from the top and the bottom, we're going to have 9 over 4. So 9 over 4 equals x squared. Okay? And then we have to take a square root of both sides. Oops. Alright, and remember, when you solve an equation like this, you have to take the positive and the negative root. So really, plus and minus 3 halves. Okay, square root of 9 over 4 is 3 over 2. But we have to take the positive and the negative because this is the square root of x squared. Okay, so that's also a pre-calculus thing. Remember, if you take the square root of x squared and you're doing that in an equation, you have to take the positive and the negative root. Okay, so that's a pre-calculus thing there. So x equals plus and minus 3 halves. remember 3 halves is 1.5, and actually negative 3 halves, that's negative 1.5, which is just a little bit outside of this interval. So actually negative 3 halves, we don't consider that because we only care about this interval, and negative 3 halves is outside of this interval, so we just don't care about it at all. So negative 3 halves we toss out. It's still a critical point because it makes the derivative 0, but it's not on the interval that we're looking on, so we don't care about it. So okay, the only critical points that we have that we care about are x equals 0 and x equals positive 3 halves. Okay, so those are our critical points. So that's it for step 1. Find all the critical points of the function on the interval. Okay, so that's usually going to be the hard part. Sometimes step 2 might be kind of difficult too, depending on the function. And actually, this function is not really terribly nice, so that might be a little messy. But all right, let's go ahead and make some room here, and then we'll continue on with step 2. Okay, so again, the only critical points that we have that we care about are, so let's go ahead and write those down. So the critical points CP for critical point, those are x equals 0 and 3 halves. And remember, negative 3 halves is outside of this interval, so we don't care about it. So now what we do is evaluate f of x, or in our case g of x, doesn't matter what we call it, evaluate the original function, not the derivative, the original function at each critical point and at a and b. Okay, so you know, why are we doing it at the function and not the derivative? Well, because we're talking about finding mins and maxes of the function. Okay, so we want to know what's the actual value of the function at each of these points. And then the largest value is going to be the max, the smallest one is going to be the min. So that's why we do the function, not the derivative. So remember, it's different if we're using the first derivative test. Okay, we have to use the sign chart and all this things like that. But it's a little bit easier here. Okay, there's less steps to follow. Okay, so critical points are 0 and 3 halves, and then the endpoints of the intervals are negative 1 and 8. Okay, so step 2, evaluate the function at each critical point and at each endpoint, a and b. Okay, a and b, negative 1 and 8. So we have 4 different values of x to plug into the function here. So we're going to go ahead and do that. So step 2, you know, most of the time is going to be easier than step 1, but it might be kind of tedious depending on how many numbers you have to plug in. But let's go ahead and see. So evaluate the function at each critical point, so both of these guys, and also at each endpoint. So g of 0, okay, we actually already found that out, but let's go ahead and write it down. We talked about it earlier, but we'll just write it down. So g of 0 is 0 to the 2/3 times 9 minus 0 squared. Okay. 0 to the 2/3 is just 0. 9 minus 0 squared is 9, so this is 0 times 9, which is 0. Alright, so g of 0 is 0. Okay, so we found that out. So we can't say anything yet, right? We have to evaluate the function at 3 halves and at both endpoints here. So now let's see, g of 3 halves, that's going to be kind of a mess. So g of 3 halves equals 3 halves to the 2/3, okay, 3 halves to the 2/3. 3 halves to the 2/3 times the quantity 9 minus 3 halves squared. 9 minus 3 halves squared. Okay, so you know, 3 halves to the 2/3, that's not really a nice number, but let's go ahead and simplify this just a little bit. So this is 3 halves to the 2/3 times, now 3 halves squared, remember that's 9 over 4, so this is 9 minus 9 over 4. So 9 minus 9 over 4. Alright. So now what we could do is simplify this a little bit. So 9 minus 9 over 4, we can multiply this by 4 over 4. Okay, so this is 3 halves times 2/3 times the quantity. So 9 times 4 over 4 is going to be 36 over 4. So this is 36 over 4 minus 9 over 4. Alright. So remember 9, that's the same thing as 36 over 4. So we're just getting common denominator here. So then minus 9 over 4. And then this equals, running out of room, 3 halves to the 2/3. 3 halves, whoops. 3 halves to the 2/3. Sorry about that. Not much better. Times 27 over 4. Okay. So this number doesn't help us out a whole lot, but what we could do is toss this into a calculator and see that it's kind of sort of approximately equal to 8.8 8, 4, 5. Okay? So 27 over 4 times 3 halves to the 2/3 is about 8.845. Okay? So now that's the function evaluated at both of the critical points, so now we have to evaluate at the endpoint here. So those should hopefully be a little bit easier. So let's do g of -1. Okay, so that's our first endpoint here, -1. So g of -1 is -1 to the 2/3. So this is -1 to the 2/3. And then times the quantity 9 minus -1 squared. Okay? So if you take a -1 and raise it to the 2/3, you're actually just going to get +1. Okay, so there's a couple different ways to think about it, but you could say -1 squared is +1, and then take the cube root, you just get +1 again. So that's one way to think about it. Anyway, so -1 squared is +1. 9 minus +1 is 8. So this is 1 times 8, which is 8. Okay? And then, so that's g of -1. Now the last one to check is g of 8. So we just did g of 0, g of 3 halves, and g of -1. Now we do g of 8. So g of 8 is 8 to the 2/3 times the quantity 9 minus 8 squared. Okay? So 8 to the 2/3, so again, a couple different ways to think about it. You could say 8 squared is 64, then take the third root or the cube root, that's 4. Or you could say 8 to the 1/3, okay, the cube root of 8 is 2, and then if you square that, you get 4. But either way, 8 to the 2/3 is just 4. Okay, so this is just 4 times 9 minus 64. 8 squared is 64, so this is 9 minus 64, which is -55. Okay, so 4 times -55, that's -220. Running out of room here, there we go. -220. Okay. So that's it for step 2. Alright, so step 2 is evaluate the function at each critical point and at A and B. So step 3, again, isn't really a step, there's nothing left to do but write out the answer pretty much. The largest value is the max, the smallest is the min. So let's go ahead and summarize what we just found. So g of 0 is 0. G of 3 halves is about 8.845. G of -1 is 8. G of 8 is -220. So which one of these is the largest? So here's -220, 0, oops, accidentally erased that, 8.845-ish, okay, for this one down here, about 8.845, and so let's maybe also circle this one up here, and 8. Okay, so g of -1 is 8, g of 0 is 0, g of 3 halves is this guy, and g of 8 was this guy. So the largest one, okay, so -220, pretty small, 0, 8, and then 8.845. This is actually the largest one here. Okay, so here is our absolute extrema. Okay, here's our absolute extreme value, okay, and it happens when x is 3 halves. Okay, so g of 3 halves gives us this. So on the interval from -1 to 8, the absolute max happens at x equals 3 halves, and it is this number here. Okay, so let's go ahead and write that down just to be thorough. So the absolute max is, so we'll say y equals, so what was that again? 3 halves to the 2/3 times 27 over 4. So it is y equals 3 halves to the 2/3 times 27 over 4. Sorry, kind of cramped in there. So 3 halves to the 2/3 times 27 over 4. I might have to get a new marker soon. Absolute max is y equals this at x equals 3 halves. Okay, so that's our absolute max, so that's supposed to be a 3. Alright, and then the absolute min is going to be the smallest. Let's zoom back out just a bit. So the absolute min is going to be the smallest of these. So it's not this one, that's our largest one. So here is 8, 0, and -220. This one by far is the smallest one. So the absolute min on this interval from -1 to 8 is this one here. It happens at x equals 8, and it is this guy right here. So the absolute min, the absolute min is y equals negative 220 at x equals 8. Okay, so remember, g of 8 was negative 220, so when x is 8, the y value is negative 220. All right, so that's pretty much, I mean, step 3 really just tells you, how to interpret what you did in step 2 pretty much. That's all step 3 says. So, step 2 is evaluate the function at all these points, and then step 3 tells you just how to interpret that. So this is our answer here. Now, if we wanted to be really thorough, I guess technically what we should say is the absolute max of g of x on negative 1 to 8 is this at that. The absolute min of g of x on negative 1 to 8 is this at that. But, for most cases this is pretty sufficient here because it's not, it's not going to be ambiguous what you're talking about. You're talking about this function here. So anyway, the point is, here's the absolute max. Here's, this is what it is, this is where it occurs. The absolute min, this is what it is, this is where it occurs. All right, and that's an example with finding absolute extrema on a closed bounded interval. So we'll do a few more in the next few videos.